Back to the channel EC TechNest. On day 12 of our 100 Days of Architecture and Verilog series, today we have a small mini project. It is 4-bit ALU and its test bench. Let us understand what is an ALU. An arithmetic logic unit is a fundamental block that performs what you can call a mathematical operation or logical operation in the CPU. It performs all the mathematical calculations and logical operations that allow a computer to process data. Think of the ALU as the engine of the processor. While other parts of the CPU handle moving data, following instructions, the ALU does the actual work of transforming the data. See, this is how ALU looks. You have a 4-bit input here and a 4-bit input here. S2, S1, S0 are called the operands or the operations that will be performed. Let us see, based on the bit value 000, the function performs addition, subtraction, then you have a minus 1, a plus 1. In this way you can code whatever operation you need to perform for this particular operand. You can put it here, and that function, whenever it is called, it will perform this operation. So we have output as 0 flag, carry flag, and overflow flag. Z is 1, that means your 0 is 1 if your function gives an output as 0. V is overflow and C is carry or borrow. We'll understand today this in a very practical way. This is your EDA playground. Let us first understand the design part. This is your module 4 ALU 4-bit. You have a 4-bit, two inputs, that is 4-bit A and B, and the operational code is of 3 bits, and the ALU output is also of 4 bits. Then you have registered your carryout, that is going to be a single bit carryout, and output 0 is your 0 flag. You also declare a temporary variable that is reg4. I'll tell you why you need this. Here you may observe that your output is just of 4 bits, but why is this temporary variable required for 5 bits? When you perform sometimes addition, you might get a carry flag or something like that. So to store it temporarily, we are using this temp variable. In the end, when we require it, no, we'll split it. The ALU output will be of 4 bit and a single bit will be a carry out bit. Let us go into the code. Always at all conditions we begin. The case statement is given based on the opcode, that is your whatever we discussed here. This is your opcode 000 Based on that, we have given some function for 000, that is 3-bit 000. Your function will perform a plus b. For 001, it will perform subtraction. 010, it will perform a logical AND. 011, it will perform a logical OR. And for 100, it will perform A XOR B. For 101, it will perform a logical NOR. And for 110, it will perform a left shift. And for 111, it will perform a right shift. And the default value of temporary variable will be 5-B00000. End case. We are ending the case here. And I'll tell that whenever there is a ALU output, that will be from temporary variable of 4-bit. And the 5th bit will be for carryout. And I'll end my always block. Later I'll assign 0. When do I call 0? Whenever when will I raise the 0 flag? Whenever my ALU output will be 4-bit 0000. We'll understand this using a waveform. Before that, let us see our test bench. Let us go here. So I have declared it as module ALU 4-bit test bench. Before that, I have also mentioned the time scale 1 nanosecond, the unit, and precision as 1 picoseconds. If anybody doesn't know how this works, please attend the day 10 lecture where I have discussed deeply about generating clocks and simulating the test benches. So here again I have 4-bit input registers, that is A and B, and the opcode, that is your input, and wire is a 4-bit ALU out, wire again single bit carry out and 0 flag. Now I need to instantiate the test bench. So what I'll do, I'll write ALU 4-bit, that's the name of my module, I'll tell this is the unit under test, and I will connect my test bench inputs with module inputs. So dot A with A, dot B with B, dot opcode. Will connect all the inputs and outputs. So whatever was your test bench is now connected with the module, that is your design, and I'll initialize. This is okay. I'll explain these two lines in the last. Okay. So I will give my display statement. So I'll display the time, whatever was my A input, B input, operand, what is my result, carry flag, and zero flag. Here I have just given the stimulus, whatever is my test cases, different test cases. Here I have only done it for 4 cases. Let me run the code. Yeah, I have received the code. Wait a minute. Okay. First, let us see how it is working here. Now that my whatever my test bench was there, it is getting displayed here because yeah, I have used the dollar display. Before that, you need to know this what test bench I have used. I have used system verilog and verilog, and here I have used iCares verilog. You can also use Aldec Rivera Pro if you have signed in, and after it, tick on the open EP wave after run so that you will get a waveform viewer. I'll also tell you how to generate the waveform. Let us wait for a minute. So, okay, now that this is displayed, time A, B, C, D, op, res, C, and Z. A and B are your input, OP is your operand, a result, carry flag, and zero flag. So, what is this? It is 8, and this is also 8 in decimal. Here it is binary. When it gets converted, it's 8 and 8. Okay, 1 minute. We'll verify this using the waveform itself. I'll press get signal. I press on ALU 4-bit. I will select all of them and I'll tell append all. Then I'll close it. So you might observe whatever was my first input, it is 8 and 8. So what is the first operand? It says 0, 0, 0. So 0, 0, 0 is addition. When I add 8 and 8, my result is 0. You might ask why. Because when we add both the numbers, the resultant output will be observed in the carry flag because the last bit is shifted to the 5th bit. So we get a carry flag. And since my result is 0, a 0 flag is also updated. Let us see whether it is the same in our output. Yes, carry out is 1 and 0 flag is also updated. Now let us see the second example. 0, 1, 0, 1. That is your 4, 5. So 5 and 5. The resulting output is 0, 0, 1. The operand is 0, 0, 1. So it means I have to do minus subtraction. When I subtract a minus b, 5 minus 5 is 0. I do not have any carry and my 0 flag is raised again because my resultant output is 0. Let us verify that again. 5 and 5, the output is 0. So carry out is also 0. But the 0 flag is raised because our output is 0. Here I have 10 and this is 12. 10 and 12. And what is the operation that I am doing? 0, 1, 0. So I am doing logical and my resultant output is 1, 0, 0, 0, 0. That is 8. Let us see whether I have got it. Yeah, this is my equation, that is A and C. All out 8 is 8, and there is no 0 flag and there is no carry flag. So the output is verified. And the last case is 0, 0, 1, 1. 1, 1 is 3 and this is 0. What is the operation? 1, 1, 0. So 1, 1, 0 is left shift. Let us see whether left shift has occurred or not. Here, okay, we have shifted it to the left, so we have got 0, 1, 1, 0. Let us verify it in our waveform window. Yes, my first input is 3, 0. and my resultant output is 6. Is it correct? 0110 is 6. So I have got here written decimal form. This is a way you can verify your outputs using EDA Playground. Whenever you write the test bench, right, try to get a table like this, so it will be easy for you to read and verify your waveform. Thank you. If you have any doubts, feel free to put it in the comment section.